Hello, ladies and gentlemen. 안녕하세요. I'm pleased to see you here back again. Let's see what the topics are. So, chapter 1 we already have finished. Then chapter 2 we finished. Chapter 3 we finished. We continued with chapter 4 using variables and assignment. Then again exploring operators and expressions, and then exploring conditional flow, and this time we continue with exploring loops and iteration. Okay, so loops and iteration. The following topics will be covered in this chapter, so chapter 7, exploring loops and iteration, understanding brute force repetition and why it might be bad, then exploring looping with the while statement, and then exploring looping with the for statement, and exploring loop with the do while statement, and then understanding when you would use each of these looping statements, understanding how loops could be interchanged if necessary, exploring the good, the bad, and the ugly of using goto, exploring safe alternatives to goto, continue, and break, and then the finishing topic is about understanding the appropriate use of loops that never end. So some operations need to be repeated one or more times before their result is completely evaluated. The code to be repeated could be copied the required number of times, but this would be cumbersome. Instead, for this there are loops: for, while, and do while loops. Loops are for statements that must be evaluated multiple times. We will explore C loops now. Now, understanding repetition. Very often we need to perform a series of statements repeatedly. We might want to perform a calculation on each member of a set of values, or we might want to perform a calculation using all the members in a set of values. Given a collection of values, we also might want to iterate over the whole collection to find the desired value, to count all the values, to perform some kind of calculation on them, or to manipulate the set in some way. Say, to sort it, for example. There are a number of ways to do this. The simplest yet most restrictive way is the brute force method. This can be done regardless of the language being used. A more dynamic and flexible method is to iterate or repeatedly loop. C provides 3 interrelated looping statements, so while, for, and do while. Each of them has a control or continuation expression and a loop body. The most general form of these is the while loop. Lastly, there is an archaic go-to-label method of looping. Unlike any other language, there is no repeat until statement. Such a statement can easily be constructed from any other as well. Now, each looping statement consists, and here you see, of the following 2 parts: a loop continuation expression and the body of the loop. When the loop continuation expression evaluates the true you get into the body of the loop, and the body of the loop is executed. The execution then returns to the continuation expression, evaluates it, and if true, the body of the loop is again executed. This cycle repeats until the continuation expression evaluates to false. Then the loop ends, and the execution commences after the end of the loop body. There are two general types of continuation expressions used for looping statements as follows. So counter-controlled looping, where the number of iteration is dependent upon a count of some kind. The desired numbers of iteration is known beforehand. The counter may be increased or decreased. Condition or sentinel controlled looping is the second one, where the number of iterations is dependent upon some condition to remain true for the loop to continue. The actual number of iterations is not known. A sentinel is a value that must attain a certain state before the loop completes. Now we will explore counter-controlled looping here and return to sentinel-controlled looping later on. Now C also provides some additional looping control mechanisms such as break, which we saw in the switch statement, also an earlier chapter exploring conditional program flow, and continue. These provide even greater looping control when simple counters or sentinel values aren't enough to meet our need in special circumstances. Now, to boost our motivation for iteration and repetition, let's visit a problem that was presented to the young, brilliant mathematician Gauss in the 17th century. When Gauss was in elementary school, to fill time before a recess, the teacher assigned the task of adding numbers from 1 to 100, or some such a range. While all the other students were busily performing the tedious task of adding each number one by one, so brute force way, the young Gauss came up with a simple yet very elegant equation to perform the task nearly instantly. His general solution was the following here. Sum of n means n times n plus 1 divided by 2. Here, n is the highest number in a sequence of natural numbers, integers, beginning at 1. So, throughout this chapter, we will explore the problem presented to the young Gauss, starting with his insightful equation, and then moving on to various programmatic solutions. First, using brute force addition, which Gauss cleverly avoided, then performing the task using each of the looping constructs C provides, and finally looping with the with a go-to statement. Alright, now the following code snippet shows Gauss' equation in some n via Gauss function. So here you have it, and the input parameter is capitalized N. The result is the sum of integer value n, so 1 and n. This function is a part of Gauss brute force program, and there are links in the program for delightful explanations of the equation, along with the variations of it, which we need not to go into. If you want to, let's do it. Why don't we just download it first? Okay, so packed. Gauss brute force C. What a wonderful long code it will be. Oh yeah. Oh my goodness. Oh my goodness. That is really something. You will see immediately. It's almost 300 lines. I don't know who made that code, but used a lot of time for this. Yeah. So okay, let's also save it as. And I put it here, Gauss brute force. Ah, come on. Let me save it. Let me save it, please. So good. See. Okay, we got it. Now let's try to run it. No errors. Good. Good news. Good news. Good news. Oh, and I forgot something. I have to switch off the virus killer during a run C here. Oh, good lord. Yeah. So. Done. And now we can run it easily. Much better. Yeah, here we go. You see, by brute force 1, by so Gaussian inside, then you see that too. Okay, let's see what is that exactly. So brute force 1, brute force 2, and then we have it. So brute force 1 is this. Plus 20, 30, plus up to 100, right? Return sum. And here you see, wow. Then you get 10, then you get 20, 30, 40, 50, 60, 70, 80, 90, 20, okay, and 100. And then you see here the shortest version of the code. So, yep. And I guess we should go and move on. Now, in the brute force repetition, so okay, so a statement or series of statements to be repeated is simply copied over and over the required number of times, which we already saw by ourselves. This is the most restrictive form of repetition because the number of repeats is hard-coded in and cannot be changed at runtime. There are several other downsides to this type of repetition. First, what if you had changed one or more of the statements that have been copied over and over? Then the next one is, tedious would be the word to describe the work required to either change all of them, so error prone, or to delete, correct, and recopy the lines, also error prone. Another downside is that it makes the code unnecessarily bulky. Copying 10 lines is one thing, but copying 100 and 1000 is another thing altogether. Okay. Now, however, there are also times when copying a single statement multiple times is actually necessary. The situation where this occurs is in an advanced topic involving loop unrolling, which we will definitely not cover this time. Okay, if you are still interested after you have finished this chapter, you can perform your own internet search to find out more, which up to you. So I myself, I'm not that interested. So it's up to you. The sum 100 via brute force function is a brute force function to perform our desired task, and it shows the following code block. You have seen that. Notice that we do not include every single line of this over 100 line function. It is very tedious and dull, yet in fact it correctly calculates the sum of 1 to 100. This function only works for this sequence and no other. You'd need a different brute force method to calculate to 1 to 10 or 1 to 50. Yeah. So here is a second version, a bit more general, using some useful C operators. So the brute force 2 function, and this is illustrated in this code block. Again, we don't use all, so we don't include every single tedious line over the 100 line function. While this approach removes the removes the need to actually type in each value from 1 to 100, it is equally tedious. I found that it was actually more difficult to create than the first version, because it was hard to keep track of how many sum plus equal plus num semicolon is included. Now you see the next one. So when you enter these functions yourself, it is acceptable in this case, but don't do it. So in the main function for Gauss brute force C, you see the following. If you create the if you create the Gauss brute force C file, then enter the main function and the three sum functions. Compile the program, and then you can get your results. In the preceding screenshot, what we already had, actually, okay, we don't need more than this here. This is too much. Okay, finally, something what is useful. Introducing the while statement. While statement has following syntax you see here: while, continuation expression, and statement body. Continuation expression is evaluated, and if it is true, the statement body will be executed, and the process repeats. When continuation expression evaluates to false, the loop will end. The execution resumes after the statement body. If the continuation expression initially evaluates to false, you don't even get into the statement body, so never execute it. The statement body is, or maybe a single statement, or even the null statement, a single semicolon without an expression, but most often it is a compound statement. Note that there is no semicolon specified as a part of a while statement. A semicolon would appear as a part of a single statement in a statement body, or would be absent in the case of the statement body consisting of the curved brackets compound statement. Also note that within the statement body, there must be some means to change the values used in the continuation expression. If not, the loop will either never execute or it will never terminate once begun. The latter condition is also known as an infinite loop. Therefore, in counter-controlled looping, the counter must be changed somewhere in the body of the loop. Let's return to Gauss' problem. We'll use the while loop in a function that takes n as a parameter, which is the highest value of the sequence to sum. So here you go, here you see. And it returns that sum of 1 to n, so 1 to capitalized N. We need a variable to store the sum that is initialized to 0. We'll also need a counter to keep track of our iterations, also initialized to 0. The counter will have a range of 0 to n minus 1. Our loop condition is the counter less than capitalized N, so n. When the counter reaches the value of n or capitalized N, our loop condition will be false. So n is not going to be less than n, and our loop will stop. So in the body of our loop, we accumulate a sum and we increment our loop. We increment our counter. When looping has completed, the sum is returned. Okay, here we have it. Then let's see also the next one. So the sum n via while function is shown in Gauss loops. We will do that this time. So let's take our new source file and let's see what we have to do exactly. We start always as usual, include stdio, and then because we need here also booleans, so include std bool.h. Okay, let's first do our prototyping. It's here. Then we need our main function, so int main. It's a void. We don't need to do more than that. Okay, and now int n is going to be 100. And print f the sum of 1 d is %d via while loop okay, new line, and sum 1 to n, 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 1 n, oops, let's stop here actually. So n via while, and again n, and we got it. Now we can do this function. Okay, int sum n via while int n int sum first 0 as mentioned, int num is 0 again as mentioned. Then the next line is while num is less than capitalized n. So again, remember num 0.99 and 100 is not 100, right? So while then do, oops, so zoop, that's it. Sum plus equal num plus 1 and num add 1, okay, and then return, here we go, return sum. I hope that this is correct until now. And should be fine. In the int mine we still need one more. Return 0. And then let's see, this is open, closed, open, closed. We are good to go. Let's try to find this out if we are good. Save as. And this time I'm saving this is a sum n via while, and only later when everything is done I'm going to do more. Okay, error, warning 0, 0. Right, 0, 0, good. Done. I'm happy. I'm really happy. No mistakes. The reason why I'm really happy is because I do separately. The book actually put up all the code in one single file. Okay, there is a bit of wrinkle. This wrinkle is known as off by one problem. We talked about this, so off by one. This problem has many forms in other programming languages and just not in C. Notice that our counter starts at 0 and goes to n minus 1 to give us n iterations. We could start at 1 and check if the counter is less than n plus 1, or we could also start at 0 and test if the counter is less than or equal to n. This second approach would give a correct answer for this problem, but would give us an n plus 1 iterations instead of just n iterations. Starting at 0 and going to say 10 would altogether be 11 iterations. There is a valid reason we have chosen to start our counter at 0. It has more to do with C array indexes, which we will encounter later again. This may seem confusing now, yet zero-based counting indexing is very consistent principle in C and also in many other programming languages. Getting accustomed to it right now will save you more on headaches when working with array indexing and pointer addition later. On the other hand, there is another way. In this second way of the implementing of the while loop, instead of counting up, we'll count down. Furthermore, we'll use the n input parameter value as a counter, so that in this way we don't need to separate counting variable. Remember that the function parameters are copied over from the caller, and also that they become local variables within the function then. We will use capitalized N as a local variable to be our counter. Instead of incrementing our counter, we'll decrement it. The valid range will then be from capitalized N down to 1. And in this way, we'll let 0 be the stopping condition because it also evaluates to false. Now our continuation expression is simply evaluating whether n is, so capitalized N is non-zero to continue. We could have also used the while capitalized N is larger than 0, which would be only slightly more explicit, even if redundant. In addition, we get some minor benefits of not having to deal with the off by 1 problem. Then our counter is also an accurate representation of the value that we want to add. Let's do this, but this time the file is also different. We need to get it in from the other one. So I'm going to check this out, and here we go. Alright, we need another file similar to this, so we will just grab this first. Let's open a new file and let's see what we have to change. Now, this is okay. Here we need to add a 2 and print f, and here we need to add a 2 again. Return 0, and we can continue with the while loop. int sum n via while 2 int n int sum while n, so n down to 1, so stopping at 0, do sum plus n and n minus minus. Okay, so again here n and down to 1 stops at 0. And return sum. Okay, hopefully this would work as well, and this time we need sum n via while 2, so I'm going to save it as well. Yeah, we got it. We got it. That's really nice, we got it. So, let's continue also with the file here. Okay, the difference is in how the count is performed. Now we don't add, we deduct. Now, is one approach better than the other? Not really, right? And certainly not in these examples, because our problem is rather simple. When the statement body becomes more complex, one approach may be better in terms of clarity and readability than the other. The point here is to show how thinking about the problem is in a slightly different way can make the code clearer sometimes. In this instance, the difference is in how the count is performed. Now, introducing the for statement is the next topic. So the for statement has the following syntax. Wow, it looks ugly. So for counter initialization, continuation expression, counter increment, and statement body. The for statement consists of a 3-part control expression and a statement body. The control expression is made up of the counter initialization, where is it? Yeah. Then expression, then a continuation expression, and a counter increment expression, where a semicolon separates each part of an expression. Each one has a well-defined purpose. Their positions cannot be interchanged. 순서대로 이런 식으로 나와야 돼요. 다른 순서로 바꾸지 마세요. So, upon executing the for statement, the counter initialization expression is evaluated. This is performed only once. Then continuation expression is evaluated. If the result is true, the statement body is executed. At the end of the statement body, the counter increment expression is evaluated. Then the process repeats with the evaluation of the continuation expression. When the continuation expression evaluates to false, the loop ends. The execution resumes after the statement body. If the continuation expression initially evaluates to false, the statement body loop is never executed. The statement body may be a single statement or even a null statement, so a single semicolon without any expression, but most often it is compound statement. Note that there is no semicolon specified as a part of for statement. A semicolon would appear as part of a single statement in the statement body, or would be absent in the case of the statement body consisting of the curved compound statement brackets. In the for statement, all of the control elements are present at the beginning of the loop. This design was initial so as to keep all the control elements together. This construct is partially useful when the statement body is either complex and we already move as well, or overly long. There is no possibility of losing track of the control elements since they are all together at the beginning. Okay, now returning to Gauss' problem, we'll use the for loop in a function that takes as a parameter, again capitalized N, the highest value of the sequence to sum, and returns that sum of 1 to capitalized N. We need a variable to store the sum initialized to 0. The counter will need to be both declared and initialized to 0. In the first part of the for statement, the counter will have the range of n to n, range of 0 to n minus 1. When it reaches n, our loop condition is the counter less than n will be changed to false, and our loop will stop. So in the body of our loop, we need to only accumulate the sum. When looping has completed, the sum is returned. Let's do it. Let's come back to our sum n via while, and let's do this as well, and let's do the prototyping as well. int sum n via 4 int n. Good, then now we can do the printf again. So printf, this should be okay via for loop, and sum n via 4 return 0 is fine. And now we only have to do an int sum n via why I don't get a capitalized F right now, I don't know. So okay, I got it finally. For int n, good. Int sum is 0, so set the 0 first, then for int num is equal 0, num is less than capitalized n num plus plus. So remember what we had here again. So for counter initialization, continuation expression, and counter increment. And then now we can continue with the statement body, which we want to do right now. no semicolon, right? Sum plus equal num plus 1, and we are done. And then return sum. Let's try to run this, but this time I'm going to change already to Gauss loops. C. Okay. No errors. Everything works fine. We got it. Okay, of course we can also change this, just as the last time. There is a second way to perform this loop. Instead of counting upwards, we count then downwards. So the second way, again, we will use the input parameter value capitalized N as the counter. So we don't need a separate counting variable. Remember that function parameters are copied from the caller, and also that they then become local variables within the function. We will use N, so capitalized N, as a local variable to be our counter. Instead of incrementing our counter, we will decrement it and let 0 be the stopping condition, as well as evaluate it to false. So, as before, we get the somewhat minor benefit of not having to deal with the off by 1 problem. The now counter is also an accurate representation of the value we want to add. Let's do it, and we will update this situation here as well. Actually, we can simply just copy this part with a number 2. Number 2, I said. int sum n via 4 2. Again, int n should be correct. They are good. And then now the 4. So int sum n via 4 2 int n int sum is set to 0 first, then 4 int I is equal a capitalized N, I is larger than 0, and I, minus minus is correct. Now let's do the same issue. So sum plus equal I, and we return the sum again here. Return sum. We update this file again, so save us. And here at the end, I already created this sum. No, what is it? Gauss loops to see let's try to run it and let's see what we get. And we got definitely what we wanted. Awesome, no mistakes again. Okay, one final thing to notice in sum n via 4 function is that the parts of the control expression are formatted such as each part is now on its one line. I didn't do that, but I could do that too. So it was like this in the book. Doing this allows for more complex expressions and comments for each part. Sure, certainly, but right now it's not that complicated. So, for example, let's assume we want to simultaneously count up and down using 2 counters. We can initialize more than one counter in a counter initialization expression by using the comma sequence operator. We can also increment more than one counter in the counter increment expression, again by using the comma operator. Our for condition might look like the following, so let's see that. Yeah, here we go. Okay. Yeah, here. However, the indentation should be used to keep the control expression clearly identifiable from the loop body. And this simple example, such code formatting is unnecessary and should only be used where the control expression becomes more complex. Exactly what I said. Introducing the do while statement is the next one. The do while statement has the following syntax this time. So do statement body while continuation expression. The only difference between this statement and the while statement is that in a do while statement body is executed before continuation expression is evaluated. If the continuation expression result is true, the loop repeats. When continuation expression evaluates false, the loop will end. Note also that the terminating semicolon. If the continuation expression initially evaluates to false, the statement body loop is executed once and only once. Returning again to Gauss problem, the similarities to the while statement are clear. In fact, for this problem, there is a very little difference between the while and the do while statement. Let's do it. So what we need here again, int sum n via do while, and again int n is our function prototyping. We can now add the printf. And the printf function, how does it sound this time? I don't remember. So sum of via do while loop and sum n via do while n is correct. Good, we can go and move on. And let's create it immediately. Actually, I could use this one here better, I guess. Okay, so sum n via do while, right? And then int sum, int num, both are correct. And here we do and this part comes in there. And while num is less than n, and actually here we stop the execution, so we don't need this curved parenthesis anymore. And I hope that this is correct this time as well. Let's see this time. If you have done the same what I have done, then you have no mistakes and you can run the code. So we got the do while here. And notice that because the statement body consists of more than one statement, the statement block is required. Otherwise, a compiler error would result. And as we have already seen before, we can revert this to decrement as well. And let's do that. Decrementing, so where is it? Dev. Good. Then I need this one first. Sum n via do while 2, right? Good. Then here again we need the next one. And it's do while loop here we go, and loop 2 and loop 2 and loop 2. And this one is n, yes, but this one is some n via do while, of course, 2. Okay, then I need this here again. Certainly I still have to work on it, but it's less than typing it. Int n, we are good. And then do this here. While n, that is correct, and return sum, so we don't need the curved brackets as well here. And we are good to go again. No. Then, oh, now we are good to go. And we got all values correctly, as I expected and as I hoped for. Okay, I correct. Basically, I did all the coding. Here you see that the book it just reworks this part later on, and we actually finished these parts already, so we can just move on. And what we do now is to stop here, and what we do afterwards is to understanding the loop equivalency. So I'm going to take this part later on and we work on it later. This time I would like to say thank you very much for your attention, and we start again. You see that here, understanding loop equivalency. That is our next topic, and see you then again for that topic. Thank you. Bye bye.